Good day, Physics 30. We're going to go over the wave model pretest here. Let's see what we have here. Yeah, this is it's a pretty confusing chapter. It's a confusing little unit that we got going on here. It's very abstract, very interesting. So let's see. Oh yeah, and they're going to talk about the photoelectric effect in some of these situations. If you do the recent news in science and physics and stuff, you'll realize that the photoelectric effect isn't the way it is anymore. This is like an very oversimplified version of what the photoelectric effect actually is. It's getting a little bit more complex. It's quantum mechanics. Quantum mechanics are always complex. Okay. So we have some incident rays here. All sorts of different wavelengths here. You got 225 nanometers. I could just change those quickly to nanometers. 233, 324, and 428. Platinum, that's commonly used to coat the satellites, have a work function of 8.5 times 10 to the negative 19 joules, which of the wavelengths will cause a photo emission, which could positively charge. So you're going to lose electrons. If you lose electrons, you become positively charged. So I'm going to pull out my calculator. Here's my calculator. It's actually my phone. Right, there's my calculator. Okay. So we are going to change all of these, or you can do it one of two ways. You can either change all of these into energies and then compare their energies to the number. If they're more than the work function, then it's going to cause a photo emission. Remember, because work function is the minimum energy. Or you could just change the work function into a wavelength and then look for the wavelengths that are lower than that, because the lower ones have the higher energy. So that's what I'm going to do. So I'm going to change this number. Let's get the right formula. I'm going to change that number into a wavelength by using the HC over lambda formula. So lambda is equal to HC over E. So I'm going to use the H, that's the 6.63 number, because that's in joules there. Okay. Then we got the speed of light. Let's put that in there. And let's divide by the 8.5 times 10 to the negative 19 joules. Okay, let's plug in my calculator here. I hope your days are going well. We're getting near the end of the year here, which is kind of nice. Days are getting nicer too. That's negative 19, right? Yeah. Okay, so I get a number that is 234 times 10 to the negative 7 meters. Okay, so that there is your maximum wavelength. It's not the minimum frequency, but it's the maximum wavelength. Any wavelengths higher than that are not going to cause photo emission. So I can always cross off right now. I cross off 3 and 4. Okay, so any wavelengths lower than this, even just slightly lower, because remember, this is the maximum wavelength. Anything lower than that would have enough energy. So 2 and 1 will be just enough for us here. So I'm going to go with C on that one. Cool. Photoelectric radiation is constant wavelength. Okay, constant wavelength means constant energy. So I'm not going to change the energy. So the photon energy is the same. Is incident on a metal cathode, and the photoelectric effect is observed. Okay, so we at least beat the threshold frequency there, threshold wavelength. Determine the following. Which of the following graphs, represents the relationship between maximum kinetic energy of the photon and the intensity of the incident radiation? So remember, intensity doesn't mean increase in energy. It just means more photons. All those photons are going to have the same energy. It says up here, the wavelength's constant, so that means the energy is constant. Okay. So each photon still has the same amount of energy. Remember, it's a one-to-one relationship. So it's not going to change the kinetic energy of each of the electrons, because the photons all have the same energy. So it's going to be A in this situation, right? None of these other ones kind of make any sense. it would make sense. B would make sense if down here, rather than said intensity, if this said like frequency or wavelength or energy of the photon. Let's say I change that to frequency. Then this would make sense, right? So this would be, well, somewhat the same kind of graph. It wouldn't be at 0, 0. No. Right, make a little bit more sense. Okay. Together, the Compton effect and the de Broglie hypothesis support, well, it supports the particle nature. Oh, together, sorry. Together, Compton and de Broglie is a wave-particle duality, right? Compton specifically supports the particle nature of light, and de Broglie supports the wave nature of particles. Right. So those two together would create a wave particle duality. It's pretty easy. Once you talk about de Broglie, you always talk about wave particle duality. So these guys go hand in hand with each other. Now, if it wasn't de Broglie, if it was just like Compton and the photoelectric effect or something, those two things together, that would just be the particle nature of matter. Solar winds is a hot plasma ejected from the surface of the sun. Plasma consists of parts of electrons, in part of electrons, sorry. De Broglie hypothesized that a moving particle charge has a wavelength that relates to its momentum, and they give us a little formula there. What is the wavelength of the solar wind electron that's measured at the speed here? So that's not too bad. Okay, so H over P. Now, that's momentum, so that's going to be just mass times velocity. Because of this is momentum, I'm going to have to use the 6.3 number. And my mass is 9.11 because it's just an electron. And they give us the speed here, 4 times 10 to the 5 meters per second. If you want to put some units in there. On my calculator, let's see, H. Is my H stored in my calculator? Hey, it is. Okay, divide by 9.11. 31, okay. Divide by the speed here. Okay, so we get a wavelength of 1.82 times 10 to the negative 9 meters. So that's actually quite small. Cool. I think that's all we need. Something like that. Yeah, cool. Source of electromagnetic radiation operates at a very specific frequency. Okay, that might be useful. And has a power output of 100 kilowatts. Okay. Which of the following rows identifies the type of EMR and the number of the photons per second that is emitted? Now, if you know anything about radios in a car, megahertz, that is the frequency of FM radio. So that is a radio. So it's got to be one of these two because it is a radio wave. So I'm just going to cross off microwave here. Microwaves run at a centimeter range and stuff. So if you were to change that, that would be a bit too large. You could change it, probably be in the meters and stuff. If I were to do this calculation here, C over F. Remember, that's just the universal wave formula. So if I just quickly do the calculation, mega is 6, right? So this is like 3 meters long. Yeah, so this is definitely in the radio waves. Yeah, too big. Okay. So what are the number of photons here? So to figure out the number of photons, first of all, it says per second. So time is going to be 1 second. Power, that's capital P, is going to be 100 kilowatts. So I'll just change it to regular watts right here. And then the energy, so using the power formula, E over T, change of energy. which is going to be power times time, is just times 1. So it's going to be 100 times 10 to the 3 joules. Okay, so quite a lot of joules here. Now, what we're trying to figure out here is how many of these photons can actually fit in there. So I want to find the energy of the photon. Because this is in joules, I'm going to do the H times F here. I'm going to be using the 6.63 number. And I'm going to times by the 95 times 10 to the 6 hertz. That's a mega. I always want to put a 3 for some reason. That's a kilohertz. Okay. So I'm going to use my H that I have in my calculator here. Notice that if you just look at that, I stored H into my calculator, so I don't have to type it out all the time. I don't know how much time that actually saves. Maybe saves a bunch, but who knows? So the energy of this photon is quite low. So you got 6.31176 times 10 to the negative 26 joules. So the really, really small amount of energy. So now you just have to figure out how many of these fit into each other. So you could use like the N formula. You could put a little N in there if you wanted to, right? You could have put an N inside there and then rearrange this equation and put the 100,000 joules on the other side. But I'm just gonna take these two over here and go that direction. So I'm gonna take the 100,000 joules and divide it by the 6.3 number that we just got. I'm going to use more decimals than that. I'm going to divide them. So 100,000 divided by this number, and I get 1.5 times 10 to the 30. So it's got to be B. Let's get rid of this. There we go. Oh, I shall write this down at the bottom here. 1.58 times 10 to the 30. Nope, 30. Cool. Okay, student investigates, or in a student investigation, sorry, a photocathode has a work function of 1.9 electron volts. It releases electrons when it's exposed to yellow light. Okay. Should work, right? So if I were to use the HF formula there, and just quickly double check here. Yeah, so this, if I were to convert this to energy by using E is equal to HF, I don't know if you really need to do this for this question, but I'm just going to quickly do that. That's how many electron volts it is. So yeah, so that does have enough energy. So you will get the photoelectric effect. And then they record, so we've got all these electrons coming out now, and then you record the stopping voltage. Okay. In a second trial, they use the same photocathode. Okay. The yellow light is replaced with a low intensity blue light. So remember what that does. That's going to change the number of photons. So less photons. So I'm just going to write that down here. Less photons equals less current. Okay, that's what that means. So less photons equals less current, because it's the 1-to-1. So less photons, less current are going to come. Blue light has a higher energy, so the stopping voltage is going to have to increase because of the blue light. What I'm going to do with that? More energy equals more stopping voltage. I know that doesn't seem right to me, but whatever. Okay. So that's what I got from trial 2 there. So trial 3 here, we use the same cathode again. A low intensity blue light is released with, or changed with a high intensity green light. Roy G. Biv. So it still has more energy, right? But high intensity means more current. Okay. more photons, more current. Okay, green light. Can't really say if we're going to compare it to the blue or we're going to compare it to each other, but green has less, because in the course, the Roy G. Biv, blue light's in the indigo violet area over here, so this is where the blue is. Oh, I missed the B here, right? So B has more energy than green. I'm just going to write this out. Roy G. Biv. So green light, or sorry, blue light has more energy. So this is less energy than blue, right? But more than the original yellow. Okay, so comparing the low blue light to the photoelectrons, so comparing the low intensity blue light, the photoelectrons emitted because of the high intensity green light require, so we're going to compare it to the blue light. So the green light requires a smaller stopping voltage because it has less energy, right? So it has to have a smaller stopping voltage, and will produce, because it is a high intensity, will have a larger current. Right. That's a bit tricky. Based on the results in the investigation, determine the maximum stopping voltage required for the yellow light. So yeah, so I needed this information up here. So what we need to know is that we have the photon energy in is equal to the work required to get the electron out plus whatever energy is left over as kinetic energy for the electrons. Remember that all of this is electron energy. Okay, so we know a few things already. We know the energy of the photon. I did the calculation at the top up here, the 2.14038. I know the work function. The reason I want to find the EK is because the formula for stopping voltage, I find my formula sheet, is, where did it go? Oh, right down there. Okay. This formula for stopping voltage is this EK max is equal to QE V stop. So we're looking for V stop here. So I'm going to go EK divided by Q. Cool. So I'm going to rearrange this formula here. So I'm just going to subtract over the work function. So remember, the work function is how much energy is required to get the electron out. My number is already in my calculator, so I just subtracted the 1.9 over to get the EK by itself. So 0.24038 electron volts. Now, to use this in this formula over here, this energy should be changed to joules. Okay, so it should be. I'm going to write that out. The reason I'm not going to actually multiply it out is going to be very evident very fast here. But you would multiply by the 1.6 times 10 to the negative 19. That's how many joules for every electron volt. Okay, that's what you would do. Then you would go over here and take that number, that EK, which you just found, which would be the 0.24038 electron volts, divide or times the 1.6 times 10 to the negative 19 joules per electron volt. And then you would just divide it by 1.6 times 10 to the negative 19 coulombs. So the numbers would cancel out. All the units would kind of work out together here. You get a joule per coulomb, and a joule per coulomb is a volt. So we got 3 sig digs, I think. There you go. 0.24 volts. Not very much at all. Okay, so a photocathode has a threshold frequency of this, and light has a frequency of 8.2. So this is more than enough. What's the maximum speed? So we're going to use the same formula we just did. Oops. The energy of the photon is equal to W plus EK. The reason I want to find that is because EK is equal to 1/2 mv squared. And V is equal to going to be the square root of 2 EK over M. Okay, so if I can find the EK, so let's find the EK. I'm going to go photon energy minus the W. Now the W is based on the threshold frequency. So that's going to be HF naught here, so F0. And the photon energy is just going to be, oops, it's just going to be HF, just the frequency of that one. So I'm going to find those two numbers, and I'm going to do this all in joules because joules are going to be important for this one, because the EK formula, the 1/2 mv squared, can only use joules to do this. Okay, so I'm going to do this in joules here. Okay, so the energy of the photon is 5.4366 times 10 to the negative 19 joules. The energy of the work function is 3.7128 times 10 to the negative 19 joules. I'm going to subtract these two numbers, and I get 1.7238 times 10 to the negative 19 joules. Okay, then what I'm going to do, I'm going to take that, I'm going to put it over. That's a weird spot to put that arrow. I'm going to take that, I'm going to put that over here. I'm just going to punch in my calculator. So 2 times the number I got, divided by the mass of an electron, and then take the square root, because if I don't take the square root, I get 10 to the 11, a little too fast. Take the square root of my answer, and I get a speed of 6.15 times 10 to the 6 meters per second. There you go. Pretty easy. The current produced by the photoelectric experiment in a photoelectric is 3.5 milliamps. Determine the minimum number of photons required every second to maintain that current. Okay, so current I is going to be 3.5 times 10 to the negative 3 amps. Okay, time is 1 second. Okay, so what we need to do is to find out how much charge passes by. And the reason I want to find the charge is because the charge is made up of electrons. If I can find how many electrons there are, then, well, it's just 1. So there's going to be a charge of 3.5 times 10 to the negative 3 coulombs. Okay. If I can find how many electrons, it's a 1-to-1 ratio. So if it's a 1-to-1 ratio, so I'll just turn that up a little bit, then I know how many photons there are. So the charge of an electron is 1.6 times 10 to the negative 19 coulombs. So the number of electrons is going to be the bigger number divided by the smaller number, because you're never going to have a fraction of electrons, so you always had to do it that way. 3.5 times 10 to the negative 3 divided by 1.6 times 10 to the negative 19. So I get 2.19 times 10 to the 16 electrons, since photoelectric effect is 1-to-1 electrons to photons, then 2.6 photons are needed. That's the minimum number, right? So of course it's probably going to be more than that, but if all the electrons were on the outer surface of the metal, that would be the ideal situation. You need this many photons to at least get this many electrons. Arrange the following in increasing photon energy. So from lowest to highest. So the lowest energy is going to be the longest wavelength, so that's going to be radio. And then it's going to go radio, microwave, if that makes sense. Then it would go infrared, There's no infrared here. Then visible light, RORG-BIV all the way down to violet, and then ultraviolet on the outside edge there. So that's 4. And then it's going to go 5, and then it's going to go 6 X-rays, and then gamma rays being the highest. Cool. I'm going to have a few more questions here. I don't know how long this video's gone. Okay. So in the Compton effect here, we got a scattering effect. So a photon comes and it scatters directly back, travels back the way the incident photon came. So because of that, the angle of scatter is 180 degrees. This is the maximum it could be. Went straight back the way it went. Right? What do we need to find here? In order to derive the formula for this, Compton must, so we went through this whole derivation in the notes here. We didn't go through the derivation, but I showed you the derivation. But he had to make this formula, he had to do conservation momentum and energy at the same time. Now, the final 2 questions here for this page are, what's the magnitude of the final momentum of the photon? And what is the final momentum of the electron? So we're going to have to use the conservation momentum from the very first chapter to do that. There's no angles here, so that's good. If there were angles, it'd be a more complex question. Well, there's 180 degrees, but everything's collinear to each other. Okay. So find the final momentum of the photon. Remember, photon momentum is equal to P is equal to H over lambda. Find the final momentum. I'm going to have to find the final wavelength. So I have to find the change in the wavelength, because that's going to be final minus initial. Then just add the initial wavelength over, and they just give you the initial wavelength here, 0.13 nanometers. So I'm going to use this formula up here to determine, it's hitting an electron, okay, to determine the change in the wavelength. So H over MC 1 minus cos 180. Remember, cos 180 is -1, so this is technically going to end up just being 2H over MC, because it's 1 minus -1. So 2 times H over MC. Now, this number we calculated before in our notes, because it doesn't really change. It doesn't depend on the photon. It depends only on what it hits. It hits an electron here. So I'm going to use the mass of 9.11 times 10 to the -31. C is the speed of light. You always use the 6.63 number in this formula, because everything's going to be in joules and wavelengths and meters and stuff. Okay, so got 4.8518 times 10 to the -12 meters. So it doesn't change very much. That's fine. So I'm going to use that down here to find my initial. So I'm going to do the change plus, or semi my initial, my final. Change plus my initial. It's going to add on, go up here just a bit so I can see the wavelength there, 0.13 nanometers, so times 10 to the -9. So what we get is 1.3, so that's the 1.3 from the question, 485. So that just gets kind of tacked on to the end there. So it just increased it just a little. It always increases. So it increases just a little bit. And then I'm going to go H divided by lambda. Remember, you always use the 6.63 number to do this one. Oh, joule seconds, my bad. Okay, so we get a momentum of, a really small momentum, but that's fine. 4.92 times 10 to the -24 kilogram meters per second. Cool. Now the final momentum of the electron. So we know the final momentum of the photon. Let's go up here and just determine what the initial momentum of the photon is. So the initial momentum of this photon is going to be H over lambda. Okay, so H being the 6.63 number. is 5, so it's not much bigger than the other one, but it's 5.1 times 10 to the negative 24 kilogram meters per second. Okay, now because one is going one way, sorry, where am I? One's going this way, one's going backwards, we need a sign convention. So let's just say that way there is positive. So this initial momentum is a positive number, but the final momentum down here is a negative number. So I'm just going to rewrite that here. So it's going to be a negative 4.92. There's more decimals. I'll use more of those decimals when I do the calculation here. Okay, so obviously momentum, just if I cover up the electrons, side, the momentum of the photon is not conserved because one's positive, one's negative. The momentum of the electron beforehand is going to be 0. So the sum of the momentum before this is going to be positive 5.1 times 10 to the negative 24 kilogram meters per second. So that means the sum of the momentum afterwards has to also end up being positive 5.1 times 10 to the negative 24 kilogram meters per second. Okay, so I'm going to take all that information down here. So the momentum of my photon plus the momentum of my electron has to add up to positive 5.1 times 10 to the negative 24. Okay, so we know the momentum of the photon, negative 4.92 times 10 to the negative 24. I don't know the electron momentum. That's what we're trying to find. Leave these positives there. Now I'm just going to rearrange this to find the momentum of my electron. So I'm just going to add over that number, because it's negative. This number plus my answer. I get 1.00 times 10 to the negative 23 kilogram meters per second. Yes. So we had to go back to our very first chapter for this because of conservation of momentum. Sounds pretty cool. Yeah, this is supposed to be an E there. Cool. Okay, in a classroom investigation, students observed that an ultraviolet source is on, and the ultraviolet radiation is incident on a polished metal surface. The metal leaves of the charge electroscope. So these charge electroscopes, you watch that video about the demonstration, he shows you what an electroscope looks like. His just had the one that went up, but you can have two that kind of flip up. So when they're charged, they're repelling each other, so they're out, right? And then when the metal discharges that, the charge decreases and the leaves will decrease as well, because gravity will just take over. Based on the observation, it conferred that this phenomenon is occurring because of the photoelectric effect. So this hits the surface, the electrons pop out, get a little photo emission here, and then the electrons from over here are just going to distribute themselves that direction as well. Cool. There you go. Hopefully you did well in that. Hopefully you did the pre-test and you tried it out and you went through and you marked it as you went. And I'll see you in the next video. Bye.